Hello everyone, my name is Renuka, Assistant Professor in Department of Electronics and Communication, Maharaja Institute of Technology, Mysore. So before getting into the topic directly, let us understand what are the course outcomes of this particular subject. The course objectives, what is the course objective? By the end of this learning process, what will a student gain? What is the knowledge that a student will gain will be called as an objective of that particular course, right? So it is basically categorized into 4 different heads. First being discuss the historical background of real-time systems and its classification, the evolution, all these comes under this particular objective. Describes the concept of computer control and hardware components of real-time applications, completely talks about the hardware and its applications in real-time systems. Then discuss the languages to develop software and real-time applications. So different kinds of software which will help to help the hardware to run in a real-time operating system. Then you have last finally explain the concept of operating system and real-time development methodology. So what are the development, their applications, and how real-time systems are there even till today. Okay. First, coming up to the introduction of real-time systems, we have historical background, then we have element of computer control systems. Real-time system, how is it defined? What do you mean by real-time systems? Classification of real-time systems, how are they classified? They are classified as clock-based, then you have event-based, and you have interactive systems. And then you have what are the time constraints involved in real-time systems, and classification of programs based on the sequential multitasking, or even it could be real-time itself. Go in stepwise sequence to understand what actually the real-time system mean, so that we can complete our first objective. Coming up to the historical background of real-time system, in 1950, Brown and Campbell earliest proposal to use the computer operating in real-time as a part of control system. So it is taken as a part of control system. If you can see in this diagram, okay, you have these are nothing but your feed forward, these are the feed forward lines, and you have a feed backward lines, okay. So this was a simple application that was initially started in 1950, where Brown and Campbell they actually published an article with this particular concept. But they were also supportive. They didn't only work on the analog systems but also on the digital systems too. So in 1954, the Digitrack digital computer, that is automatic flight and weapon control system, did come into being. So which means that the first ever digitized the control system actually started in 1954, especially in air control operations, okay, for the military system. So what happened during that period, there were some drawbacks in that aeronautical application for air control servicing. So all the manufacturers and the company people, they try to find certain outlets to sell their product, and one of such outcome of this particular Digitrack digital computers was in 1958, which was Louisiana Power and Light Company in Daystrom computer for plant monitoring. So this was the first, we don't even call it as a digital, or we don't even call it as a complete control system, but it was just a monitoring system which was designed in 1958. But it never had any operation to control the valves in any industrial application, though it was a power corporation. In 1959, Annan first industrial control system in Texas company RW300, that is Ramo Woolridge company at Port Arthur refinery in Texas, they came across, they started with the closed loop control system. It just happened to monitor the complete plant instead of actually controlling the valves. 1959 to 60, BF Woodridge Company, acrylamide plant, Clavard City, Kentucky and 40 other systems based on RW300 were supervisory control system, and they used only for supervision of the plant. Okay, it was not a complete control system. Okay, that was for a simple plant which was set up in Kentucky, and in the year 1959 to 60. They used a steady state optimization calculation to determine set points. For standard analog controllers, computer did not control directly the movement of valves or any other plant actuators. So they had a certain drawbacks there because they only used for monitoring purpose. They didn't actually have any control systems being adapted in this particular era, that too for a supervisory control system. 1962, the first direct digital control DDC computer system was Argus 200 system at ECE ammonia soda plant Fleetwood, which was in UK, as a provision of 120 control loops and 256 measurement. So this is considered to be the first control system ever developed in 1962. So here in Fleetwood, they had about 120 controllers and about 256 measurements that they actually designed for, but they used only about 98 such controllers, and 224 measurements were actually incorporated in this plant in Cleveland. So in 1961, Monsanto Company DDC project at Texas City startup with what is called as hierarchical control system in a petrochemical complex. This is another region in which DDC was implicated in Texas City. So earlier it was between the comparison between the two controllers were between RW300 computers and Ferranti Argus 200. So there were certain differences between the two. So here in Ferranti Argus 200, they used a ferrite core store to hold the control program. But here in 300, they used to store all the control programs on a rotating drum. Okay. So in 200, they use PROMs, that is programmable read-only memory, and use physical intersecting pegs into plug board, where each peg represent a bit in a memory word. It was laborious process, though reliable. So which means that in this ferrite core storage program concept, they had what are called as pegs. Pegs are nothing but a digital data where it will be plugged on a plug board. So each pegs which would be inserted on the board will have a capability to store 1 bit of data. So think about, if it is a 8-bit, you need to have to peg 8 times onto the board. Though it is reliable, the information is not lost unless you just dislodge, dislodging of the pegs are done, only then the contents of the information is lost. Else it was more useful, and it was reliable too. But the only drawback here was it was laborious and it is very time consuming. And when compared to 300, this was not that reliable when compared to your 200. It was slow and limited access of memory. Here you have a rapid memory access since it was digitized. Next, once you have the information, how would you safeguard your information for how long? Correct? That was the next evolution that took place. So the security enhancement by using special power supplies and switch over mechanism to protect information held in main core stores. So the security enhancement took a vital role in after the ferrite core, wherein the information the store program where all the programs would be actually stored in a ferrite core. So next would be the security. So there were 3 important headers in which they were actually thinking about the security policy. What was that? The first, in case of an industrial application, it was the valve demand. What is the valve demand? How efficiently can you switch on and off from certain process? Control systems from one to another phase, and that would be called as a bumpless transfer. So there is actually no hindrance between the transfer between one controller to the another controller. Next was the challenge was about the memory calculation. The memory calculation is loss is tolerable, soon will be updated and only slight disturbance in the plant. So if there is, for example, say about 0.2 seconds of delay at the input, at the output due to the internal or external issues, there could be a delay of 5. Okay. So if there is a delay of 0.3, then that would be taken as a feedback to the input and there will be a variation, isn't it? So the corrective measures has to be done within the control system, and that delay has to be very small so that it should not affect the entire operation of the plant. So that is nothing but your memory calculation, and what is the amount of memory that is required to overcome such errors. Next, after having all the valve memory calculation, next will be about the retention of the information. How long will it retain? How long or the extension to allow for optimization may require improvement in the maintenance for a long period of time. How long can you retain the information? So under these three headers, the information and the security enhancement was thought. The thought process actually started with all these three important headers. Next, in 1960s, we had what is called as combined core memories and drum stores, and the drums actually eventually they became hard disk drives, and the best example of them were IBM 1800, CDC 1700, Xerox Sigma series, and etc. So after this, after invention of the ferrite and the drum, the concept of merging both of them came into picture, and then they were the next step, the challenges were taken forward. So the development of software when both DDC and supervisory control were used in a computer. So now we are talking about a control system, it could be manual control system or it could be automatic. Automatic in the sense how a computer could actually control the entire process of a plant, right? So the development of software when both DDC and supervisory control were used in a computer, and quality of coding increased because it was not just about the storage in ferrite but also using a drum, which is an external hard disk, which is replaced into an external hard disk now. So now the quality of the coding also increased as well as the complexity also increased. So we used to have another concept called as switchover mode. So switching off the core contents, the program from the ferrite core to the drum and from the drum to the ferrite core came into being. So not all codes would be stored in core memory. Swapping of these codes between drum and memory and the core memory were also incorporated. Next were the general purpose real-time operating systems, and high-level languages were developed like process Fortran compilers. So now we know that Fortran was earlier called as low-level languages, but to develop from a machine-level language, which is all about ones and zeros, which was tough, and you could only design one or two because the number of activities would be concised, the limited activities, because it need lot of process involved, correct, to get 1 bit of data, 8 bits of data. But now the complexity increased. As the complexity increased, then there was development of low level languages like that of process Fortran. Okay. In 1970, 2 computers as a system, one as a standby if there is any failure during the event. So next was, as soon as you have the storing capability, swapping of the program from one to another, next will be how many such programs can I control, how many computers can I have? Can I have more than one computer in a system? Can I have more memory space? So these were some of the questions that were being answered later. So one computer with 2 processors came into being when in the year 1970. So where one were taken as a standby when the other was working. So when there is a failure in that event, automatically one switch off and the standby will come into picture. So next was the IC integrated circuit and construction of circuit boards increased in reliability, reduction in cost, and increases in the process speed. Okay, so we know that integrated circuit invention was the greatest set through for the modern day communication system or any other communications or streams of biomedical, or it could be engineering, medical, all sciences, because the important thing was the integrated circuits where you can have embedded systems. All the components were placed on a single chip, and then you could have lot of applications, enormous data storage, and then that is the era which is called as a golden era of electronics. So then in 1974, microprocessor, distributed computer and control systems came into being, where the best example is that just like mini computers. So mini computers were actually started in year 1974 with microprocessors, and later where microcontrollers came into being. So after looking at all the evolution of real-time systems, it is not just a day or two. It was about 2 decades starting from 1950s, correct? 50s, 60s till 70s, 74. So it didn't happen in just one day or two, right? So it took a lot of years from a simple supervising system, monitoring system, then hierarchical system, and then was the what you call it as the monitoring system, and then came the control systems, correct? So there is a complete evolution from a simplest to the most complex real-time system that you can see in today's life. So the entire process can be explained with a simple example of a plant. So it's called as element. What are the elements of computer control systems? So if you just see, it is the simplest plant, and that plant is nothing but a hot air blower. How will it be operated? What is there inside it? What is the end product? What is that we are expecting out of a hot air blower? Now, a hot air blower is what? It has to produce a heat or the temperature controlled hot air should be blown, correct? Hot air should be blown. That is the major entity, isn't it? But what is the plant? If I consider this as a plant, okay, a simple plant, what is the functioning happening inside a simple hot air blower? Let us try to understand the simple plant of hot air blower. This is a centrifugal pump, okay, this is a centrifugal pump where it blows air which will be heated by this heater, okay, and there is the air flow, and it ends at a thermistor bead which is terminated across, one of its end is terminated across the bridge circuit as an amplifier, other as a temperature measurement which will be between 0 to 10 volts, okay. And this temperature here would be controlled by the power input DC from 0 to 10 volts. So as and when you vary the input voltage, the temperature can be varied. You have this filament which will get heated up, and all the air that is blown through this blower will be heated, and this heat air will be got at this end. So this will become the outlet, this will be the inlet, right? So now if you just see here, you have the entire centrifugal pump here which blows the air is controlled by a motor, okay. The operation of this complete inlet air inlet valve will be controlled by a motor, and this motor will run at a constant speed, okay. And there you have an input provided. These are the logical inputs. One is on, off, okay. If you switch on logical high, then you have the motor being running. If it is off, it is 0, logical 0, the motor will be off, okay. Then you have another logical expression here where you can control the movement of your motor, whether it could be clockwise or anti-clockwise. So this becomes a controller. These are the two controllers which are given to the motor to rotate at particular speed, either in a anti-clockwise or clockwise, or switching off and on the motors. Next, here you have the inlet air which will be controlled with the help of what is called as a potentiometer. So this potentiometer, what will it do? It varies okay, and due to this driver you have all the, this entire shield, the blower has a opening. This is a fan, so it opens, okay, fully opens there and then it closes. Okay, this what the arc what you see is the inlet space for the air that will be driven in, correct. So the inlet air, the positioning of this particular field here, what you see, the blower, it will open or it will be closed, and that will be controlled by your a simple potentiometer. Okay. So now by controlling the inlet air, you can actually hot air that will be delivered out at this outlet point. And here you can also see another point called as an mainly used by the operator. You have auto, manual, heater and air inlet. Okay. So this cover here, it completely opens and closes. That can be also manually operated by an operator. So he can just press on this manual and he can just vary the potentiometer here to let air in, completely closed or completely open here. Okay. He can set the angle for the air to blow. So that can be a manual operation to let the air inlet. Other is by the temperature. You can control the inlet temperature. So the heater will be, the filament here will be, heated through this thyristor unit. So that can also be controlled by an operator. Okay. Then you have what is called as a auto operation. So when the operator don't want to actually manually hold or control or monitor the plant, he has an option to set it to auto mode. So now we need to think, what is this auto mode? Okay. So who is coming into picture when we talk about auto? We always think about a software which is need to be adapted in this hardware unit so that a computer can control all these operations. What are the operations here? One is the air inlet operations. So when an operator don't want to actually hold or monitor the entire plant, okay, he can switch over to auto mode. What is an auto mode? Auto mode is nothing but when you just switch on to auto, then you have a computer, and if you have a computer, there is a programming. So the entire plant has to be, there should be a software program written to control all these hardware units in his absence, correct? So then you can switch on to the auto, and this should be done seamlessly. Okay, or you can say a bumpless transfer needs to be done from manual to auto. So now we'll just look into another slide which talks about computer control of a hot air blower. So here, when do you get this computer? When we are talking about writing a program to actually control or monitor the entire activity of the hot air, right? Hot air blower. So here you have, first before even you think about computer control, as I've told you earlier, we have to divide the entire process into 3 different heads: monitoring, controlling, and then you have the actuators. So now you have to decide whether the inputs are, in the monitoring system, you need to first decide what are the inputs that we are going to give. Is it analog or is it digital? If it is analog, what are the inputs? Okay, here in this example, we can always think about air as one of the air inlet, okay, as one of the analog signals. The heater, okay, the switching on of off heater is also an analog. Okay, the temperature now is a analog. Now what are the digital? Digital is logical 1, logical 0, that is given to motor as a controller, external controller to drive the motor into on or off position, or clockwise, anti-clockwise, and also for inlet of air, fan in, fan out, right? And closing and opening of the complete cover. So these are some of the basic digital operation that is performed during monitoring. So monitoring is what is the present state of the plant, present state of a plant to be monitored. Next is what is nothing but the control system, as I've told you. So you need to have analog to digital and digital to analog converters, because the input here is, though it is analog, correct, it has to be digitized, controlled, the program to be written, it has to be digital to analog conversion has to happen, and then you have the control system, right. So, this is about your control computer control of hot air blower. So, if you just still simplify the entire block diagram, we have what is called as generalized computer system. In this generalized computer system, you have input devices, output devices, and you have a computer and a plant. So, plant is nothing but the industry or whatever the component that you are going to design, right. Then from there you have the input devices being connected, then you have a computer which controls, having all the software programs that controls and gives you the output, okay. The output devices gives the output to the plant, that is the product, fine. So, this is the standard I/O operations which will be connected to your computer. So, next finally you have what is called as a generalized computer control system showing hardware and software interfaces. So, if you just see the entire block diagram here, these two dashed lines actually is nothing but the interfacing unit. What is this interfacing? It interfaces between the plant and the entire computer. So, whatever the input images that is generated here is nothing but the state of the plant at that instant, okay. So, input task actually replicates the input program. What is the input task? It is nothing but it gathers all the information from the input devices and then sets up a screenshot at the input of the controller. So, this screenshot gives you the clear picture, and based on this controller task it will be given to the output image, and this output image is nothing but the present condition of this input image, okay. And this will be reviewed every time as and when there is a input given through from the plant to the controller, and from this input image you have output task, and this output task can again connected to output device, and this is a cyclic control system, and this is how you are going to have an interfacing between an external plant and the computer. And this is all about the complete evolution of how a real-time system has evolved and how we have actually the digitized system, what we call it as real-time operating system. So, in the next class we shall study about or try to define what do you mean by real-time systems. Thank you for listening.